Okay, so this week we're talking about class templates, and this week also marks the midway point of the course content. So we've completed 6 weeks of content. We've got 6 weeks of content still to go. And so this week's lectures on class templates, and then next week's lectures on custom iterators are basically for subjects or the areas that we need to focus on for assignment 3. And assignment 3 is creating a generic graph library, and I mentioned it very briefly last week, and the tutorial for assignment specification is online. And it'll probably be a good idea to read through it to get the idea of what you're going to be asked to do. Now, class templates follow on from function templates that we looked at last week. And in function templates, we saw the idea of things having type parameters, and these type parameters being keywords like T that we can substitute in a particular type when we want to. So we looked at the idea of creating these min functions, whereabouts we could take the min of an int or of a double just by having one function that was templated, and it was a prescription to the compiler to compile different versions of the template as required in the user code. And the same idea applies to class templates. So in class templates, say we want to create a stack, and we want to create the stack to be able to hold an int or create a stack to be able to hold a double. And without templates, we'd have to go and create a number of different classes, say an int stack class and a double stack class if we didn't have templates. And part of that is also because the class names can't be overloaded. So function names, we could create some sort of function. One function takes in an int, one function takes in a double. They have the same name and are overloaded. We can't overload class names. And so it gets very confusing having an int stack and a double stack and a string stack and all those sort of things, because the implementation of these things should be the same. You'd expect them to be the same. And so you're wasting code by having 20 or 30 or 100 different versions of them. And so the next few slides, there's going to be a lot of code on the next few slides, and this code is available on the course homepage. And I'll keep it up on a second screen so that you guys have the idea of what we've got in common. But a class template looks very similar to a function template. You're just going to see the word template in a whole lot of more situations. So we've got an interface here, the stack.h interface, and this is a generic stack class. It actually extends the stack class that we saw a couple of weeks ago. And this stack class is basically wrapping a vector. Okay? And now the stack class that we had a couple of weeks ago, off the top of my head it was storing ints, okay, but that doesn't really matter. We had a stack from a couple of weeks ago. This is exactly the same class, only it's been made to be generic. And so what we have going on here is we've got the header file, it's got the header guards that we need to stop problems whereabouts the class gets defined twice. We have a forward declaration of the class. So forward declaration of the class previously might just have said class stack. In this case, the forward declaration of the templated class has the word template in front of it. And type name, a bit like we would put double or int or float if this wasn't a templated class. We are forward declaring our overloaded output stream friend function. Okay, so it's got a forward declaration on it, and it's not because this function is strictly a template. Actually, it is. But the reason why this is a template is because what it takes in is a template. So we have a forward declaration of this non-member, but this friend function. That's a templated function. So it's a templated class declared, there's a templated function declared. Now we go into the actual declaration of what the class is going to contain. Okay? Again, template, type name T, class stack. Okay, so we're going to go into this now. In public, we say that this function up here is a friend function. And then we have push and pop and top, and for const version of top and empty. And three of these, 5 functions here, are templates. They take in a templated class. 2 of these, pop and empty, they're not templated functions, but they are part of a templated class. And so when we generate a templated class, these functions will be generated for the particular class instantiation that we've got. And also in this class, we have a standard vector. Okay? And standard vector is taking in type T. So when it comes to compiling this class, whatever type you declare the stack to store, that T is going to be replaced by whatever that type is. So if you're creating a stack of ints, that T will be replaced by int. If you're creating a stack of doubles, that T will be replaced by double. The compiler will do that for you. And so last week when we were talking about member functions, not member functions, sorry, templated functions, we said that the templated functions were a prescription or a recipe to the compiler to generate functions of that particular type. Exactly the same idea. This is a prescription or recipe to the compiler to generate classes of a particular type. And I'm just going to skip really fast through the next couple of slides because they're just a whole ton of code, and reading code is incredibly boring. But implementation of the class, so declaration there, implementation, remember the implementation for templated functions and templated classes go in the header file. Okay? Basically, these are just a whole lot of templated functions. So this should be very easy to read, given what we did last week. Template just goes in front of all of these things. With the exception of, see, pop over here, even though pop isn't strictly itself a templated function, because it's part of a templated class, it needs to have the word template in front of it, because this type name T here is helping resolve the scope. So I'll say that again. The function pop isn't actually a templated function. It doesn't do anything with template, but it needs to have the word template in front of it because it's part of a member function of a class. It's a templated class, and to resolve the scope, it needs to know it's part of the stack T scope. Okay? And so all the rest of this works. Okay? Trust me, this works. You can download it. You can compile it yourself. I'll just scroll up on the screen here. Okay? All that is declared on the right-hand side. The same thing applies with our output stream, overloaded friend function. Remember from a few weeks ago, this isn't a member function, this is a non-member function. This function, this overloaded output stream, is outside of the class's declaration, but it's part of what we'd call the class's interface. So the friend function is part of the class's interface. It goes in the same .h file. And again, that's a template, takes in type T, and basically prints out our stack. You can print it out however you like. In this case, it's just printing out each of the characters with a space between them. Yep.
Can you do it similar to Java where you just have template T at the top?
No.
Curly bracket
No. You cannot do it like Java. You cannot do just the type at the top and have everything else, assume that it works. No. The whole compilation process is quite different to how Java compiles stuff. It needs to be declared on the top of everything. You'll just get used to putting template type name T everywhere. Okay? Yep.
But you can type diff that, right?
You can type diff that, kind of. You can type diff a particular implementation. So like an int stack, you could type diff to be int, but you can't type diff for declaration bit. For template type name T, you cannot type diff that bit. Okay? Because that's got nothing to do with the type declaration of a particular instance of it. That's got to say this is a templated function or this is a templated class. So it's a keyword. Okay? So if you know about type diffs, you can type diff around types. You can't type diffs around keywords to the compiler. Okay?
If all the template functions have to go in our .h file,
Yep.
this expose model implementation detail?
Yes, and we discussed it last week.
Um,
So the question was, putting all the templated functions in the .h file, doesn't that expose our class's interface, our class's definition? Yes, so we discussed that last week. We had, last week, for second half of Monday's lecture, we went into half an hour of talking about that problem, okay? So, when you're dealing with templated classes, everything needs to go in the .h file, okay? Because the compiler needs to know at the compile time for user code how to generate these particular functions. And if you go and look at assignment 3, what assignment 3 asks you to submit is it only asks you to submit, where's it got to? Here it is, your graph.h. Assignment 3 submission, you're only asked to submit a .h file. All your code goes in that .h file, okay? So templated classes are different to normal classes. The declaration and the definition need to go in the header file, okay? So this is how you might go and use the stack. So our stack user hash includes our stack.hpp file. And what we have here is we've got 3 stacks being declared. We've got a stack of ints being declared. We've got a second stack of ints being declared, which is copy assigned or copy constructed into it. So here's 2 different stacks of ints. Okay? And the code that we just quickly went through, it didn't actually have any constructors defined for it, or move operators defined for it. And that's fine because the compiler-generated ones in this particular case work. Okay? And they work because this is a value-like class. Okay? So a value-like class copies the data into it. Value-like class copies the data into it. And again, assignment 3 asks you to create a value-like class. Again, if you've forgotten the difference between a value-like class and a pointer-like class, a couple of weeks ago we had some slides on that. Go back and take a look. Okay, so this code that we've shown you is very simple code. It's a basic stack for a generic type. It can rely on the compiler-generated copy constructors, default constructors, destructors, etc. Okay, but if you wanted to define them yourself, this is what they would look like. Again, they've got type name everywhere. For instant that you define your own copy constructor, you're going to have to go and define for default constructor. You've got the move constructors. You've got for assignment operators. You've got the move assignment operators. And you have the destructor, which doesn't do anything. For assignment 3, again, it's your choice if you use the compiler-generated ones or your own ones. Okay, so assignment 2, you had to go and define your own copy and move controllers. Assignment 3, it's up to you. Your code just has to work. And so that's partly why, with test cases down here, you'll see that there is some copy construction, copy assignment test cases that you should go and take a look at and see if your default compiler-generated ones work or don't work on them. So if we start to talk about the compilation model, okay? Last week on the Monday, we, again, in that long half-hour discussion at the end of the class, one of the things that we talked about is the way in which the compiler separates out compiling and linking code. And so when you're compiling code, say your Euclidean vector from assignment 2, you might compile your Euclidean vector.cpp, which hash includes your Euclidean vector.h file, and create a .o file out of that. Then I might come along and compile my test1.cpp file, which also hash includes your Euclidean vector.h file, and I create a test1.o file. So now I've got 2 .o files. And then the linker comes along and links together that .o for test1.o file with the Euclidean vector.o file. Okay, so I've got my library files, I link them together. Separate compilation, separate linking process. Again, people said last week that they weren't aware of how that worked. On Friday, I went and put a link up down here to, it's still very hand wavy, but a nice, if it loads, a nice article about how the compilation and linking process works. If you go take a look at this answer in here, it goes into a whole lot of details about how the pre-processing works, how the compilation works, and how the linking works. Okay? If you're confused on these next few slides, this is what you should go take a look at. Now with our template class, like we said, it's all defined in the .h file. And the reason for that is because we can't generate the actual object of the class until it's instantiated in memory, which is caused by the user code. So in this situation here, imagine I've got this. I have my stack.h, my templated class, and I have two user files. User file 1 creates a stack of ints and a stack of doubles. User file 2 creates a stack of ints and a stack of chars. When I go and create user file 1.o, when I go and compile that, okay, what happens? When I go and compile user file 1.h, how does this compile? What happens? Can someone tell me?
It goes and replaces the hash includes stack.h with the type codes of stack.h.
Okay, so yep, the first step is it goes and replaces the hash include stack.h with the exact copy of that. Yep, so you've got all that prescription for how to generate the stacks in there. What happens next?
It instantiates some versions of your stack class, and each version is double version.
Okay, so after it's hash included, it now goes and creates a whole class for the int version of the stack, and then goes and creates a whole version for the double version of the stack. Okay? And now we have user file 1.o. Okay, that's the easy part. Let's go and do user file 2.h. How does this compile? The same? Well, almost. Only you have now a class of ints and you have a class of char. Okay? So user file 1.o has now a compiled out class of ints and a compiled out class of doubles. User file 2 is a compiled out class of ints and a class of chars. When you link these two .o files together, both of them have instantiations of the class for ints. But that's okay, for linker can work that out. The linker can work that out, and it ends up behaving if there was only one instantiation of stack int, even though it's been instantiated multiple times. Okay? This is fine. This is how a linker works. But you've got to be careful. This is why we use namespaces and things like that. If user file 1 hash includes stack.h, okay, it declares a templated class stack, and user file 2 hash includes a different stack.h that also declared a templated class stack, but the code was actually different, but the namespaces and all that sort of stuff were the same. When you went to go and link that, the linker would get very, very, very confused because it's like having two variables int I. I've got two instantiations of the stack that are different. Okay? So it's about namespacing and header guards and stuff are very, very, very important because you need to be very clear about what you're doing. Okay? Now also, compiling templates can be slow because you're having to go and generate out all this code. Okay? Because the template is a prescription for how to generate stuff. It's not the raw code itself. So compiling, say, test 1 for the Euclidean vector, and then test 2 for the Euclidean vector, and test 3 for the Euclidean vector, I'm not having to go and recompile my Euclidean vector.o file multiple times because it's created once. With the templated class, every time I compile something, I have to go and generate the instantiation of how those classes work. And in very big programs, this can start really slowing down your compilation time. Instead of your compilation time taking a couple of seconds, a compile might take half an hour. Okay? On very, very big amounts of code. Assignment 3, that should compile in about 2 seconds. Probably faster. So let's talk about instantiation. Templated classes like templated functions are instantiated at the point at which they're called in your code. So when it says, or when the compiler sees stack int, like that, it instantiates a class for int type. If I create stack char, but it's only a pointer to the stack, the class isn't instantiated, okay, because it's only a pointer. But when I start to use that pointer, so I say PS pointing to push, character A, then the whole stack goes and gets instantiated. Now, it's pretty obvious that this code here wouldn't work in real life because we don't actually go and create the PS object, okay? But the point at which the class of a member function is required is the point at which it instantiates, okay? And so instantiation is the generation of a class from a template. There is on-demand instantiation. Again, this is part of the reason why I've given you 14 test cases for assignment 3. The reason for that is when the class gets instantiated, not every single piece of the class gets instantiated. It gets instantiated as required. So when you call the push function at that point, the recipe for generating that function gets instantiated. Okay? So it means that it's a lazy instantiation. If I never call the empty function in my code, the empty function won't be instantiated at all. If I call the empty function only on my char stack, it will generate the empty function for my char stack, but it won't for my int stack. Okay? So the compilation process is lazy. It only generates what it needs. Yep.
Can you just force the compiler to generate it anyway?
Can I force the compiler to generate it anyway? You probably can if you use the explicit keyword that we looked at last week. Okay? But if we don't need it, we don't need it. Okay? So if the compiler tries to only generate things that are needed. Okay? This is mostly a good thing. It just means that ensuring that your code is doing everything that you want it to do means that you require quite detailed test cases to test every single member function as it comes out. Again, this is why I've given you 14 test cases for assignment 3, because I'm trying to test every single piece of functionality. Well, I'm not trying to. I'm trying to give you the idea of how to test as many pieces of functionality as possible. There is some stuff missing from the test cases, which you should hopefully be able to figure out. Okay? I'll give you a giant hint. I've given you copy construction tests. I haven't given you move construction tests. Okay? There's things like that you'll need to work out yourself. But so for coming back to the class templates, they're only instantiated, functions are only instantiated when required. Okay? So this means that you can have syntax errors in your code, you can have bugs in your code that you might not realize at compile time, you won't realize until runtime, or you won't realize until you compile a particular test case. Okay? So testing is really important. Let's talk about name resolution. This is the same as function templates. Okay? So say I'm compiling this code. What happens here is I'm inside for member function push, and I print out and say, okay, here's the value to be pushed. Okay? Now, this first version is just taking a const char, well, it's taking a string. Okay? And so this is type independent, okay? It doesn't depend on the templated type. So this is resolved when the template is defined. If you do something wrong up here on the type independent code, you'll get a compile time error. For standard cout item, remember item in our stack class, is of the templated class. This will be resolved when the template's instantiated, which will still happen at compile time, but the error will look slightly different, okay? So there's two different places that things can go wrong there. One is the type independent name, the stuff that doesn't rely on the template, and the second thing, the item, which is actually of type T, the error will happen when it's instantiated. So say, for instance, this print here. I go and create some int stacks. I can standard C out an int perfectly fine. Say I go create some double stacks. I can standard C out a double perfectly fine. Both of those things will compile, no problem. I then go and try to standard C out, what kind of standard C out? I go and try to standard C out a book object, okay? So we did a book object in the tutorials a few weeks ago. Maybe the book object doesn't have the output stream operator overloaded. At that point, creating that stack of book objects is not going to compile. Okay? Because this line here relies on this thing to be overloaded. Okay? And in a particular class, it might not be overloaded, therefore that particular code doesn't compile. That may or may not be a problem with your code. It will depend on what you're doing with it. In the case of assignment 3, you are required to have templated nodes and templated edges. For both the nodes and the edges, you might need to do some sorting. The general rule for sorting is you need the less than operator overloaded. And so for that reason, I wouldn't give you a test case whereabouts the templated class I pass in doesn't have the less than operator overloaded. Because otherwise your code just wouldn't be able to work. So there's this balance between what is your responsibility as developing a templated class and what is the user of that templated class's responsibility. Okay, and this name resolution side basically just explains what I just showed you there. Okay, so the less than, so overloaded output redirection operator will have its problem after instantiation. Okay. Now, when we're talking about member functions, we went into quite a few slides, particularly on Thursday last week, about type deduction. And so with the templated functions, we didn't have to explicitly all the time tell it what version to use because it worked it out from its call parameters. Okay? Do you think I can just create a stack just like this, stack S? Who thinks that this is going to work? Anyone? No. This does not work because it can't deduce, it can't work out for instantiation of what type that should be. Okay? So there's no template argument deduction for class templates. There is for member functions. So there's for there is for templated functions. There's not for templated classes. Okay, so all that stuff we looked on Thursday to do with templated argument deduction, that's for templated functions. It's not for templated classes. But one of the other things that we looked at on Thursday was type conversions and how the type conversions for templated functions are limited. So if we have a templated function that takes in doubles, we can't just pass it in ints. You'd have to typecast. So there's limited type conversion. With member functions for classes that are templated, there is for normal templating rules. Just to really confuse you, the problem is flipped. Okay? So say I create a stack of ints like this. I then create a short and I create a normal int. When I push that short onto stack, first of all, the push function is instantiated as required, and instantiates correctly the int version of it, not for short version. Correctly instantiates the int version, and then it type converts the short up to the int, and it's fine. Okay? If this was a templated function, okay, so if this wasn't inside a class template, if this was a templated function, we would have ended up with a push templated function that takes in a short, and on the next slide we would have ended up with a templated push function that takes in a int. Okay? So for conversions, for member functions, for classes that are templated work different to the templated functions that we were looking at last week. Okay? So normal type conversions are allowed. However, member template functions, okay, so functions that are within class templates are still function templates. And again, we explained that earlier with a POP. Even though the POP isn't relying strictly on the type T, okay, it still requires to be a template because it's part of that class. Okay, we clear up until this point? Okay. So now what we're going to do for the rest of today and potentially for the rest of the week is we've built a templated stack class. We're now going to modify it, and there's going to be a whole lot of templates and modifications that build on top of what we've just looked at. So we've just looked at the stack class and built a basic template around it. Now if you remember that basic stack class that we just saw, what it internally stored was a standard vector. Okay, what it internally stored was a standard vector of type T. We can pass the templates default arguments. And what a default argument does is if we don't explicitly say this is what T or S or Q or P needs to be, this is what it should default to. And so at the back of Thursday's lecture, we looked very briefly at one of the slides about doing the default arguments for a templated function. This is going to be doing the same thing with a templated class. And so what we've got is we've got exactly the same class here that we had a minute ago for stack class, only the difference is we want to pass in the type of container that it should store values in. It should wrap around. And so whereabouts before, we had a container of vectors. This one is storing a cont. And a cont is just a type name that gets passed into the template. The default argument for this container, or this cont, is a standard double-ended queue of type T. And so what we can do with this default argument template is we can create, like we saw before, the user code before will still work. We can still create a stack of ints. We can still create a stack of doubles and all those sort of things. And if we don't tell it what container to use, it will now use a double-ended queue. But what we can also do, and I hope it's on the next slide. Here it is. Yep. I can now give it a second argument which tells it what container I particularly want to wrap around. So again, I can create 3 stacks. I create stack 1 as a stack of ints, exactly the same as before. So the code that we had before worked fine. I can now create a second stack. And a second stack, I'm going to explicitly tell it to create a stack using a double-ended queue of ints. And I can say S2 is equal to S1. Now remember that S1 by default was using a double-ended queue. Stack 2, I've explicitly told it to use a double-ended queue. For instantiation of this code, the class int stack double-ended queue will be generated once. And so a second instantiation will create me a second object of that first instantiation, okay, because they're the same class. They're the same class template. And so the assignment works fine. And we're going to come back to talking about assignment either later on today or always on Thursday. The third line, however, creates a stack of ints whereabouts the internal container is a vector. Okay, so now I've created the third stack. Still a stack of ints, but it's a different instantiation of the class template because a second argument going in has changed. I've told it this is a stack of ints that stores the value inside a standard vector. So this third stack is a different stack implementation, a different class to what was created before by the template. Okay? So I've now got 3 stacks, okay? 3 stacks, 2 instantiations of the template. So 2 different class objects. And so I can push some stuff onto the first stack. Stack 1.push, stack 1.push. 2 items go in. I can then say stack 2 is equal to stack 1. Okay? And that will do the copy assignment. I cannot, however, do stack 3 is equal to stack 1 because one of those stacks is storing the stuff in a double-ended queue, and the second stack is storing for items in a vector. Now, remember how the default copies work. They literally just do the direct copy assignment. Okay, so even if we didn't have our own custom copy constructor at this point, or copy assignment operator, that's not going to work because one of these containers is a stack and one of them's a double-ended queue, and you can't say a stack is equal to or assigned to a double-ended queue. It doesn't make any sense. Okay? So we're going to come back and look at what's called template parameters in the next lecture, okay, which is either this afternoon after a break if we get there, otherwise it's Thursday. Okay, we're going to look at how to solve this problem. Okay? But just keep in the back of your mind, we've got a problem here. Okay? So we've created a stack whereabouts we can tell it what internal container to store. However, now we've got a problem of these 2 things can't be equal or can't be assigned to each other. Now, the next few slides are just going to quickly explain how you do bits and pieces of just standard C++ that we've seen before. So one of the things that we can look at is static members, and you don't use statics that often. But the key thing to remember is with static members, each instantiation of the class template has its own set of static members. What this means is if we go back a slide, whereabouts we had these 3 stacks here, and I said there was 2 instantiations of the class there, okay? If these classes each had static members, say that original int stack containing double-ended queues, okay? Say if we were counting the number of stacks that had been generated, that counter might be at 2. We then create that third stack, where that third stack had a standard vector as being what it contained. The static member for that class instantiation is probably going to be sitting at 1. Okay? So static members inside classes are based on each instantiation of the class template. Okay? Just still in the back of your mind, you don't need that for assignment 3, you don't need that for the exam, unless you end up doing something in assignment 3 it particularly requires it. Okay, so say we've got a slightly modified version of the stack, whereabouts we've defined a destructor, if I can find it. Okay, so say that we define a destructor into our class here, okay, and a static data member, and this destructor is going to tell us the number of stacks that have been generated when the destructor gets called. Okay? And then I go into my code and I create a float stack, I create an int stack, and I create an int stack that's containing a standard vector. What happens is this float stack, this first one that got generated, well, there's one of those when it gets destroyed. There's 3 int stacks using the default parameter we passed in, which was the double-ended queue. So when those get destroyed, okay, that prints out 3. And for the 4th one, remember this is, even though it's an int stack, is containing the stuff inside a vector. One of those is going to have been created. So that gets destroyed. So even though in that code I've got 5 objects in memory, I've got 3 instantiations of the class template. Okay? And 3 sets of static members for each of those instantiations of the class template. If we talk about friends of classes, there's 3 types of friends that can be to class templates. There's ordinary friend functions and classes that we've seen before. There's friend template instantiations, and there's friend templates. So an ordinary friend would be like this. We've got a class foo. Foo is not a templated class. Foo is just a normal class. We then have a templated class for stack. Okay? I have a feeling that this is, oh no, that's fine. So I've got a templated class here. Okay? These ordinary friends, what this is friend class foobar, okay, is if I had, I think that's missing something. Basically, I can have a normal friend class, okay, so that should be friend class foo, okay. If I have a templated function also called foo, I can have friend void foo being a friend function, and I can have a friend member function, so friend void foo : bar, okay. And so these are ordinary friends. Each instantiation of the class stack will be friends of this non-templated class. Let's talk about friend templates though. So we actually want to be friends with another class that's also a templated class. Each class instantiation will be friends to every possible instantiation of that second class. Okay, so if we have a template type T here, okay, so a templated class called manager. Manager is friends with a class called task, whereabouts that class task is also a templated class. You can be friends with every single instantiation of that particular second class template. Okay? And so that works fine. Okay? Again, you may or may not need to do this in assignment 2. In assignment 2, you'll definitely need some friends. Okay? Computing ones, not real life ones. But you'll definitely need friends for assignment 3, okay? But they may or may not need to be of a different class type. They may just need to be normal types. And we'll talk about that probably next week. So the friend that you need to have in assignment 3 is you need to be friends with your custom iterators. Okay? You can also be friends with a unique instantiation of a particular class that's also a templated function. So if we go back to this previous slide, this type name T and this type name U here are different types, or can be different types. If we only wanted to be friends with a particular type that is the same as our type, then what we do is we just keep the same type name. So type name's T. That's going to be consistent, okay? And so inside this code, say class stack here, we can say we're friends with class foobar type T, and that T and T there match up. The same with the normal function template, and the same with the member function template, okay? For example, we saw before with a stack and the friend function for overloaded output redirection operator is another example of this. Okay, so three types of friends. First type is ordinary friends like we've seen before. The second one is where we've actually got many friends because the type is going to be different. And the third one is trying to get a one-to-one mapping between your instantiation of a particular class for a particular type and another class that's going to have the same type. Now, just again, basically filling your brains with stuff that you'll need later on, there's this keyword called type name. say I have a class, I'm going to start halfway down this code. So, say I have a class Y, and inside this class Y is a nested class, which isn't a template, okay, but a nested class called ID. Okay? A nested class called ID. Okay? I then have a class X up here, and X has a pointer to this nested class. And this nested class as well could be contained within some sort of template. Okay? Because this T isn't actually a real type, it's just a filler for that type to be substituted later on. When I'm declaring a variable of that type, if there's a subtype within it, so it's in a class here, I need the word type name. Now, normally for compiler, when you go and run this code, if you need to put type name in places, the compiler will tell you. And often it will give you an error, and the error for type names are pretty good. The error normally says, oops, I think you're missing a type name. You should go put a type name in here. You go put a type name in there, and normally your code will compile. If it doesn't, you'll end up with a whole other page of errors. Okay? But for compiler with type names, it's quite nice. They're used for nested types. And you'll probably be smacking into these problems again in assignment 3. Because assignment 3, you probably need a nested type for your node, and you probably need a nested type for your edge. Again, it will depend on how you've written your code. But assignment 3, you shouldn't be exposing the inner workings of your graph. So you shouldn't have a graph, and in a second class that is your node, and a third class that is your edge, that are all sitting out by themselves. They should be nested within for one graph class. And again, if we get time on Thursday, I might show you how to do a bit of templated nested classes. If not, we'll do it in tutorials next week. So in summary, for the introduction to class templates, templates are used extensively in the standard template library, okay? And we've been using them all semester, but now we're going to go and write our own class templates. They're relatively straightforward to understand. They just build on top of ideas of the function templates that we've been looking at. But their syntax can be overwhelming. The reason for that is suddenly you've got T and Q and P and R all over the place, okay? And also the error messages can be overwhelming. Be prepared for when you have an error to get a wall of errors, hundreds and hundreds and hundreds of lines long, okay? It's very, very, very annoying, but the compiler tries to be helpful. It thinks that if you have an error, it's going to spit out every single possible thing that you could have possibly meant. It's trying to help you. It just, by the time it spat out 1,000 lines of that stuff, it's not being very helpful anymore. So basically, write a few lines of code, compile often. And you'll often discover you'll have some sort of error that's caused one of these things, and you take that line back out, and suddenly your code compiles again. And so fixing these templated errors can be quite difficult. Again, this is why I've given you so many test cases for assignment 3. Okay? But templates really go to the heart of how C++ works, and this is why we're spending so much time looking at them. Okay? Again, there's some readings that you can take a look at in your own time. At this point, I'm going to stop for about 7 minutes, and I'm going to resume at 1 o'clock. Any questions before we do that? No? Okay, take a 7-minute break. Okay, so let's resume. So what we're going to look at over the next hour is breaking class templates and member function templates down into more detail. Okay? And so let's first of all look at some STL code. And so in this STL code, I've created a vector of ints, and I've created a list of ints. And what I can do is I can create a vector of ints with 10 here, okay, and it's going to create size 10 vector. And I can create a second vector and copy assign it, and that works fine. If I go and create a standard list, and I try to assign it that vector, it won't compile. And the reason why it won't compile is because one's a standard vector and one's a standard list. And this is exactly the same problem we had an hour ago, whereabouts we had two instantiations of a stack class and we couldn't assign to them if the containers were different. But what I can do is I can create a standard list by passing in an iterator to the start of a vector and the end of a vector, because the constructor exists for this. Okay? I can also create or call the member function of the list, the member function called assign, and also pass in the vector's iterators, and that will exist, or that will work, because the member templated function exists. Okay? So standard list is able to handle items to standard vector. And so what we're going to be talking about now is how do we handle templated functions within templated classes. Okay? Now, if we go back and take a look at what we did an hour ago, we had the default argument stack, whereabouts we're taking in this container argument being the type of container that this stack should wrap around. And by default, it wrapped around a double-ended queue. But we could change that so it wrapped around a vector or a list or something else. But we had this problem of if we had a stack of ints, one of them was storing the ints in double-ended queue. We also had a stack of ints, one of them was storing them in a stack of vectors, or container vectors. You couldn't copy assign them. And we want to know how we can do this. Okay? And so here's the same code again. If we create a stack of ints and a second stack of ints, it works fine. If I create a stack of ints and a stack of floats, well, I can't copy construct that because there's no constructor for that situation. I can't assign it because there's no assignment operator for that type of situation. I can't pass in the begin and end on the iterators because we don't have that type of constructor. And I can't do the assign because assign doesn't exist. Okay? So in our code, we can't do what that code in the standard template library does. But we want it to. And so to support member templates, we have to define some additional stuff. And to do that, we add some stuff into our class's declaration. Okay? So into the class's declaration for default arguments, okay, we might add some additional templates and template function declarations. Okay? And they might look like this. So I've got this code on both screens at the moment. We have our class template inside the declaration of this class template. Okay? I have templated constructors and templated functions. Okay? So I've got type name T2 and container type name container2. Okay? And so what I've done is I've gone and created a default constructor because I need that default constructor for the rest of my code still to work. I then have a copy constructor that takes in any other stack object, even if the type it contains and the container storing that data is different. The same thing with a move constructor. I can now define my iterator versions. I can define my copy assignment and my move assignment. And I can now create this member function called assign. So I'm adding all this code into my default argument stack. To then make this code work, I end up putting template all over the place. Okay? So now I have the top one is referring to the template class and the second one. So if I take a look at template type name T, type name container, that's referring to the templated class. And then the second line being template type name T2, container 2, that's referring to the member function. And so I've got a templated member function within my templated class. And it's starting to get quite confusing at this point, isn't it? Okay, so here's my constructors. Okay, Let's very briefly take a look at this. Is the copy constructor. Okay, so the copy constructor is coming in, creating a temporary version of the stack being passed in, copy assigning or copy constructing a temporary version of the second stack. What we're then doing is we're going through this temporary object and we're just moving or copying everything across. Okay? When we say stack underscore dot push front temp dot top, this could be two different types. That temp dot top could be floats. The stack dot push could be int, and there's a type conversion going on there. So again, the type conversion operators need to be defined for this code to work. But again, this code might work in some situations and might not work in other situations, and this is why you need to test your code pretty thoroughly. This code will work for inst to floats and inst to doubles. This code will not work if you have a container of a stack of ints and you've got a stack of strings, because you cannot convert just using the default type conversion operators or typecasting an int to a string. Okay? So there's nothing wrong with the code at this point. The problem that you might face is your use of the code in your own classes later on. But this starts to get very ugly and very confusing very quickly, as you can imagine. Okay, so here's some more code. Okay, this is the same on both screens. Okay. Also remember that there's lazy initialization. Okay, so the vector, standard vector does not have push front defined. Okay. And so you can still use the vector as the internal container. Perfectly fine. Provided that in your code you avoid assigning to a stack with elements of a different type. So you could still create a stack using a vector container, okay? But remember our initialization of these templated member functions inside the templated class rely on this dot push front being declared for the internal type, okay? What this means is we cannot have a standard vector and have a standard vector get passed in a standard list. We can do it the other way around. We can have a container that's storing stuff inside a list and pass it in a vector and it'll be fine. Okay? It's a minor point for now, but member templates cannot be virtual. Virtual's to do with polymorphism and inheritance and stuff that we'll look at in coming weeks when we start to look at object-oriented programming. Okay, member templates can't be virtual, okay, which is to do with they can't be overloaded. Sorry, they're not overloaded, they can't be extended, okay, because they can't build a V-table, which is how it handles polymorphism, okay. Ignore that last point until we come and talk about object-oriented programming. So now, using this member template stack, we can write some code that will go and first of all create an array of floats. We can now use the constructor of stack to go and handle that perfectly fine. That works. We can use the assign member function. That works fine. Okay. I don't know why the next line is commented out. We can go create a stack of ints, and we can assign that stack of ints the stack of floats. And that works because we now define that member template constructor. And again, we can do the same thing with copy assignment. Okay, so now all this code that didn't work half an hour ago works perfectly fine now. Okay? And we can do the same thing with move semantics, and the move semantics work perfectly fine. Okay? So it works with both copy semantics and move semantics. Okay? But we've got a problem. Got two problems, actually. First of all, this code is really confusing. Who's confused with the template sort of stuff? It's horrible, absolutely horrible. The second problem that we can get into, that we may or may not want to get into, is this type conversion problem. Okay? We can perfectly fine at the moment go and declare a stack of ints, and for default argument, we overwrite to be a standard vector also containing ints. We could create a stack that's supposedly meant to take in floats, but for container it stores the stuff in is a standard vector of ints. And we could create a stack that's meant to take in ints, but it stores it in a container that actually stores floats. This code will compile and it runs. But we have problems, as you can imagine. And the problems are these. The first one runs fine because we push 1, we push 2, there's no issue. The second one, we want the stack of floats, but we're telling it to store it inside of a container of ints. And so we push 1.1, we push 2.2, and this is fine, except for when you go to print it out. And when you go and print it out, the output is 1, 2, because the float that you pushed got stored into a container of ints, and therefore did a type conversion, and you lost that data. Okay, the data got narrowed. Third example, you have a stack of ints, and you push 1.1 and 2.2 onto that. Okay, that's fine because it's going to be type converted from a float down to an int. You then store it in a container of floats, so that thing that you just narrowed from 1.1 down to 1 is now going to be converted back to a float, but because you've narrowed it, it stays at 1.0. And so when you print this out, 1 and 2 comes out. And that's not the intended behavior. What you want us to do is you want us to give it the template type of the container it should have stored the stuff in, but there's a matching that needs to go on between the type of what you're giving this thing and the type of which it's storing the thing. And so the idea is we prefer to write stack int comma vector being as a stack of ints and the internal container being a vector, rather than having to write stack int vector int. Okay? Because the T element, the generic type T and the container are related. But at the moment our code isn't handling that. Okay? And so how do we fix this problem? This is the question that we're going to ask. How do we fix this problem? Okay. So we're going to use a thing called template parameters. And so the code up on slide 3, which I'm just going to quickly bring back up onto the right-hand side, we're going to modify this code to, rather than taking in type name T, type name container, which might be a double inner queue, okay? We're going to modify this code to have a template that has a nested template inside it. Okay? So template type name T, comma, template type name T, and then what we're doing is we can give it the default argument at that point. Now in this case, this has actually been modified from vector or double inner queue to a standard allocator. It's just a different type of container you can use, but it still all works. Okay, so we've got this nested templates. So template type name T, comma, type name whatever the nested template is. Okay? So take a look at this code very carefully. It is slightly confusing, okay? We've changed the templates up on the top, okay? So the blue lines are things that have changed. Okay, we've had to change our friend function. We might have had to have changed our container down here. So on our previous container, if we go look at this, and this is going to be a right-hand screen, okay? So you're not going to see this if you're only looking at the left. On the right-hand screen, before, our default argument stack just had container in there. Okay? On this version, our container is now typecast to be of type T. Okay, so it's template code. See the difference. Container, oops, you can't see my finger here. Container here, okay, like that. On this version, it's taking in the type T. And so these types are inherently linked, and so this is going to fix this bug that we've had before about we could end up mismatching our types. Okay? So a template parameter is a template parameter that is in itself a template. Now, when we go and write this code, what we can do is this. We can say stack int, comma, standard vector. And we don't pass that standard vector for type anymore. The rest of our code goes and works out for instantiation of this stuff. Okay? And so this fixes our bug at this point. And this code is cleaner and easier to read. Okay? The client code is cleaner and easier to read. Your code might look a whole lot of mess because, as you can see up the top of here, if you look at line 9, you've got template, type name, type name, class. Okay, so this becomes quite a big mess on your side. But the user using your template is doing two things. First of all, their code is easier to read. The second thing that's happening is you're protecting your code from bugs. Okay, because you're forcing those type T's to be the same. Okay, we clear on this so far? Yep.
Would it be a bad idea to hash define that long?
Would it be a bad idea to hash define that long thing? Yes, it would be a bad idea to hash define that long thing because you're hash defining.
Right.
Do not hash define. Hash define, again, go read about how pre-processed macros are working. Hash define is a raw cut and paste. It loses all the type checking. Okay? Hash define is inherently evil. Okay? There is, again, examples. Go back to looking at this stuff here. Somewhere in this big list of links is a link to do with how macros are evil. It should be, oh, right there, right in front of me. Week 6, macros are evil. Go and read this. Okay? So yes, even though you have always templates all going over the place, hash define is not your solution to this problem. Okay? So let's talk about specialization as well. Say we have a stack class, okay? And we want to give a specialized version of the stack class for when we have pointers. Because pointers, we should already know, work differently to normal types. Okay? We saw this last week, where we had to define a partial specialization on the, or not partial, we had to define a specialization for a member function to do the minimum of two things when we're talking about char stars. This is a this is a partially specialized template type or class for stacks of templates. Okay, so suddenly we have T stars going everywhere. Okay, now partial specialization is a bit of a weird name. Partial specialization of a class is actually a full redeclaration and redefinition of that class. The reason why it's a partial specialization is because the type coming in is still a generic type. Okay, so we haven't done, we'll talk about a full specialization in a minute. But this partial specialization is still a templated type, it's just for a particular type of template or particular types of classes. And we'll, again, next week when we talk about custom iterators, we'll end up talking about type traits and talking about how we identify particular properties of types. Okay, but this partial specialization of the stack class works for pointer types. Okay? It's a full rewriting of the entire class. And so you should provide exactly the same interface and exactly the same behavior as you would for the normal type. Okay? Because if you don't, it's going to be utterly confusing. But if you wanted to, you could provide partial specialization of this class and give it a whole different set of behavior. Your stack, you could completely redefine to be a double-ended queue or just a normal queue. It'd be really, really dumb, but you could do that, okay? But partial specialization allows you to create a particular, still templated version of your class, but for where there is a particular type trait that you're trying to identify and you're trying to write a particular code to handle. So in this case, we're writing particular code to handle pointer types. Okay? Full specialization is when we provide a full non-template class for a particular type. So say I wanted to create a stack class exclusively for Euclidean vectors. Okay? This is a full specialization. So previous slide, for template still had the type name T and the class stack, but just that T star was suddenly there. This one, we've still got the template here, but we've lost all the type name bits. And so this is fully specialized because what we're doing is we're defining the exact type that this is taking in. So this is going to be a specialized version of the stack exclusively for Euclidean vectors. Okay? And again, like I just described with partial specialization, your full specialized class might have different members, but it's usually bad to do so. Okay? The reason for doing this is, again, you might have particular types that might not work with your normal code. Say if you're talking about some sort of stack container that relied on classes to always have the less than operator overloaded because you need to sort them. Say you're trying to create a stack of a particular type that didn't have the less than operator overloaded. If you did not fully specialize the type out for that particular class, your code wouldn't compile. Okay? So specialization is used for when particular types that you know are going to be passed into your templated class aren't going to compile under normal circumstances. That's where you use specialization. Okay? Now, this week's tutorial is going to talk a little bit about specialization. Okay? Actually, I'll load up and I'll show you a little bit of this week's tutorial now. Okay? So this week's tutorial is based on function specialization. Okay? But similar ideas are going to be explored in it. And one of the questions I got asked last Thursday was, with the template specialization for member functions, couldn't you just operate overload? And I went away and had a bit of a look at that. And for the most part you can, but very occasionally you can't. Okay? And I was going to give you a scenario where you couldn't, but it was a pretty extreme edge case. Okay? So I'm not going to give you that example. But instead what I have got for you is a template where there's two functions, and one is a normal template which says print if whole number, pass in type T. And if this template gets called, well, nothing prints and it returns false. So this template is going to assume that whatever's being passed into it is not a whole number. I then have a specialization on when the type is an int. And when the type is an int, then it prints it out and returns true. Okay? And so in the case of function templates and specialization of function templates, I could just lose the template bit there and I could just make it an operator overload. In the case of specialized classes, you can't do this. You need for template specialization for classes. Okay? Now, I am making a bit of a point about this because there will be a couple of questions in the exam to do with template specialization. Okay? So, this week's tute is important. Next week's tute will also be important because these type of questions will come up in the exam asking you what is the behavior. Okay, it's not going to be these exact questions, but they'll be asking you what is the behavior of this code. And so it might even be, it's not, but it might be similar questions to what will this template do if it's given a string, a double, or Euclidean vector? What will this template do if it's given an int? Now, hopefully this example should be pretty straightforward to work out. And again, for tutorial, we'll go into more details about it, okay? But specialization is important. It's for when we have a template that we know isn't going to work in particular edge cases, and so we define those edge cases manually and how to handle those edge cases manually. We could also specialize particular member functions of the class rather than having to specialize the class as a whole. So what we've just seen with a partial specialization and with a full specialization, we've seen a full and a partial specialization over the whole class. We can do a specialization just on member functions of the class. So say if we had this push command inside our stack, and remember our stack is a value-like stack, and so a value-like stack always copies the data. If we are pushing const stars onto our stack, so we're pushing constant strings onto our stack, because those are pointers, the pointer is going to be copied, not the value that it's pointing to. And so in this situation, we might need to push a specialized version of this function, okay? So we can define a specialized version of particular member functions when we know there's going to be edge cases that they don't work on, okay? So you don't need any of the specialization stuff for assignment 3, at least you shouldn't. No, you don't need any of the specialization stuff for assignment 3. You will need to know how the stuff works, at least very high level, for the exam. And I don't necessarily expect you to have to write code to do this. I expect you to be able to interpret the code, and be able to read the code and understand the ideas behind it. So why you need the specialization, why or what does this code look like, and how do you read this code? Okay? So you can take a look at this in your own time. But what this is this is an example from a book called Thinking in C++. You can actually download the book for free from the internet. The Thinking in C++ book, though, is about 15 years old now, so it's doing some more old-style ways of doing things. And so this is an updated example, okay? But it shows you how the specialization works. And so what we have here is we just have a class that we've called sortable. This class sortable extends or inherits a standard vector. Okay, you don't need to not worry about for now about how this extension works, but basically it's just an extended version of standard vector. The reason why you might do that is a normal vector, you do not have a function called sort. You can pass the vector into standard sort, and that's what you should be doing, but by default you don't have a member function .sort on a standard vector. And so this is how you might add a member function for .sort to a standard vector. Now, the normal templated function for sort, you might just do a simple sort. Okay, and that code, don't have to care about how it works, but that code goes and does a sort. Okay? But again, we end up in this problem of pointers. And so we might provide a partial specialization for pointers. This partial specialization is over the whole class. So we've got a whole separate specialized or partially specialized class at this point. So previous slide, class sortable. Next slide, class sortable T star. Again, the whole inheritance works again. And then here's our specialized version of sort, which is doing dereferencing to make sure sorting on pointers works correctly. It dereferences the pointers to do the sort correctly. We can then do a full specialization for, say, a standard string. And the reason why we might want to do this is maybe when we're sorting our strings, we want them sorted by length and not just by characters. Okay, maybe we want them sorted by length and not by characters. What it means is I could have a string A for maybe, I don't know, 80 characters. I could have the string B, and I want the string B to come before the string A because the string B by itself is shorter. So if you look very closely through this code, we have a normal class, we have a partially specialized class, which is a full separate class, but the specialization is done on the type, on the pointer type. And the third side here, the full specialization, note very quickly, this is not a full specialization of the class as a whole. This is a full specialization of the member function. And so that's why it says template like that, void, sortable. This is taking in a string. This is the sort version just for string. It's a full specialization just for standard strings. Okay? Again, this is starting to get really complex at this level. Okay? And so I don't expect you to necessarily write this. You can write it if you need to. Okay? But I expect you to understand how these things work and how to read this code. That's the important thing, is how to read this code, how to know what the output of this code should be or what you'd expect this code to be. Okay? If you don't understand this, definitely go and take a look at this week's tutorial. Okay? And there'll be more examples as we get closer to the exam, but there's definitely exam questions on this partial and full specialization. Okay? And how you might run this code, again, there's just a whole ton of code on these slides here. Okay? I'll actually put it up real quick. Okay, I was going to make. And so I'm going to go and compile this code. Shouldn't take too long to compile. Okay. Here we go. I'm going to run sortable user. Okay. And so what this code did, let me clear the screen. Run again. So what this code does is sortable user. Okay. It first of all generated some random numbers and put those random numbers into our stack, and then sorted them. Okay. It then created some char stars somewhere in this source code down here. Can't quite see where it is. Okay, I can't see quite where the code is, but created some code for using the char stars. So we've got for words short and long and longer. Okay? And so when we did the sort using the partial specialization on pointers, okay, it dereferenced the pointer down to what it was referring to and sorted that way. So that's how come we end up with long, longer, and short. Okay? Now, actually, I'm going to pause. What do people think will happen if I don't do the specialization on the pointers? If I go and disable the specialization on the pointers, what do people think the output of that code is going to be? So the short, long, longer, what do people think is going to be the output if I don't do a partial specialization for pointer types? Should be easy. What do people think it's going to be?
Solve the addresses?
Yep, so what's the output going to be? I'll do it in a minute, but I want you to guess. Who thinks the output, if I don't do the partial specialization, is going to be short, long, longer? Okay, who thinks it's going to be long, longer, short? Yep, a couple people. Who thinks it's going to be something else? One person? Okay. The answer is it's either going to be the first one or the later one, depending on how my computer works. Okay? We'd expect it to be the first one. We expect that the sort just isn't going to work at all. Okay, so let me just quickly bring up the code here. Okay, sortable.h. Let me disable for partial specialization. Let me go and make this again and run it. Okay. That's really surprising. So the output was actually in the end something else. So whoever put the hand up, I think it was one guy who said it would be something else. It ended up being for something else. Do you know why?
Just the order of initialization of the pointers.
Yep, it's for order of the initialization of the pointers. Well, actually it's not. It is and it isn't, okay? So when you create a pointer, it goes into memory. And so the default sort on the pointers there is just sorting on memory address, okay? Now, what we can expect, generally, what we can expect, is those pointers are going to be sorted in hopefully increasing order of memory. but it depends on the computer. And so in this particular case, my computer has decided that even though it created short, long, longer in that order, when it went and actually put the stuff into memory, somehow longer has ended up in memory before long ended up in memory. Okay? If I've written this again, I may get a different output. Nope, I got the... Did I get the same one? I've lost short, longer. So I got the same one in that situation, but I can keep running this multiple times, and I may get different output depending on exactly what's going on inside the memory on my system. So this is why we need to do this partial specialization for pointers, because this isn't behaving as we expect it to do. Okay? So I take this back, I make this again, and it works fine. Does the optimization have something to do with it? Most likely. Okay? If I took the optimization out, would I get different answers? Let's try. Okay, let's put that back into there. In the make file, let's go and change the flags to take the optimization out. Let's make. Let's run. Okay, so short, longer, long, no, the optimization in this case didn't have anything to do with it. Okay, but it could do. You're exactly right. Optimization can also do interesting things with the memory. Okay. Now, again, if we look at this further, we've got for full specialization for standard string. Okay, even though the output there says partial, it's actually full specialization for standard string. And again, if I disable that full specialization, you'll get a different output. So I disable for full specialization. I recompile. I run this, okay? Now I get the same output as just using the pointer dereferences, but remember that standard string, I said I wanted to sort them based on length, not on the actual character by character value. Okay, so that full specialization now changes the behavior. Okay, we clear on how the stuff's working? Okay, so again, I'll just repeat myself, okay, but the highlight here is not so much that you necessarily have to go and write this code. I think it's too complex, okay? But what you should be able to do is you should be able to see what this templated with the square brackets, so with the angle brackets just without any arguments going in is doing, and be able to interpret that. And again, this week's lecture goes into this detail. Okay, so at this point, this is basically what I wanted to cover off for today. What we're going to end up doing on Thursday is looking at a couple of things. We're going to probably move what we call advanced templates out until after mid-semester break. And instead, we're going to look at more of the structure of how you do nested templates to push you more towards how to do the third assignment. The reason why we're pushing you towards doing the third assignment early, or saying to think about now, is the third assignment is due at the end of the mid-semester break. But the issue with the third assignment being due at the end of the mid-semester break is you may or may not get the support from the tutors and stuff the same. The other reason why we're pushing this stuff through now is we're going to give you assignment 4 as well before the mid-semester break. Assignment 4 is going to be due at the end of semester, so you will have quite a lot of time to do so. Okay? The reason why we're pushing that forward is because the mid-semester break occurs at the end of week 9, and then at the start of week 10, we have Labor Day. And so we lose actually 2 Monday lectures. Okay? And so we're going to push the assignments out a little bit earlier, give you the content that you require for the assignments, and then we're going to spend for 3 weeks after the mid-semester break talking about advanced topics. And there will be a lecture on the Monday of week 13 for revision. So the Monday lecture we lose for Labor Day, we will have a Monday week 13 revision lecture, okay? So that concludes today. Is there any questions at this point? No? Okay, I'll see you guys on Thursday.